Hello everyone. In the previous class, we have studied the working of JK flip-flop. Now we will study the characteristic table and excitation table for JK flip-flop. As I told you in the previous video, characteristic table is nothing but we will be having the the previous output and the present input, and we will be predicting what will be the next state, or what will be the next output. So that information is given by characteristic table. So before going for characteristic table, we should know the truth table for JK flip-flop. I'll just write the truth table for JK flip-flop. It is having two input J, K, assuming the clock is equal to high. Output of JK flip-flop, I will take output as Qn plus 1. That is nothing but the output of next state. Since I'm having two input J and K, I will be having the four combination of inputs, that is 0, 0, 0, 1, 1, 0 and 1, 1. So when it is 0, 0, it is memory state. That means the previous output will remain. So that is nothing but Qn. That is nothing but I'll get the previous output. If next output is Qn plus 1, I'm taking the previous output as Qn. If Qn was 0 in the previous state, you will get 0. If it is 1, you will get 1. 0, 1, output is 0. 1, 0, output is 1. 1, 1, you will be getting the toggling state. That means if Qn was 0 in the previous case, you will get it as 1. That is nothing but Qn bar. So this is the truth table for JK flip-flop. So by having this truth table, let me construct the characteristic table. So characteristic table, the inputs are previous state and the present input, and my output is next state. So I will be predicting what will be the next state by having the different combinations of input and the previous output. So since I'm having the three inputs, I will be having 8 combination of inputs. Yes. So when j is equal to 0, k is equal to 0, look at the truth table. What is the output? When j is equal to 0, k is equal to 0, output is qn. So what is our qn here? Qn is 0. So the output is 0. When j is equal to 0, k is equal to 1, look at the truth table. J is equal to 0, k is equal to 1, output is 0. So here it doesn't depend upon the previous output. When j is equal to 1, k is equal to 0, output is high. When both are 1, 1, what is the output? When both are 1, 1, it is Qn bar. So what is our Qn? Qn is 0. So Qn bar will be equal to 1. Once again, when j is equal to 0, k is equal to 0, output will be Qn. So what is the value of Qn here? Qn is 1. 0, 1, it is 0. 1, 0, it is 1. 1, 1, your output is Qn bar. Qn bar is nothing but complement of 1. So it is C. So this is the characteristic table. Okay. Next is excitation table. So in excitation table, I told you we will be predicting the minimum number of inputs which is required to excite the output. That means I will be having input as my output here. That means I will have Qn and Qn plus 1 as input, and I will predict what will be the value of J and K. I told you excitation table is very important whenever I'm designing the counters, especially in counters we will be using JK flip-flop. So excitation of table for JK flip-flop plays a very important role whenever I'm designing the Modian counters. So two inputs are Qn and Qn plus 1. So it is 0, 0, 0, 1, 1, 0, 1, 1. So four combination of inputs I have. Now check your characteristic table and fill out the excitation table. So what is the combination of input? 0, 0. So when Qn is equal to 0, Qn plus 1 is equal to 0, what will be the value of J and K? See here, two combination of zeros are there here. Qn is 0, Qn plus 1 is 0. What is the input? J is fixed. J is equal to 0. K may be 0, either it might be 1. So J is fixed. K may be 0 or 1. So I'll write it as don't care state. Clear? So next I will take the combination of, next combination is 0 and 1. So Qn is 0, Q bar is 1. So Qn is 0 in these two cases. Qn plus 1 is 1 in this case. So what is the input? J is fixed as 1. K may be 0 or 1. So that means J is fixed. K may be either 0 or 1. Right? So next combination is 1 and 0. Check out the combination of 1 and 0 in the characteristic table. So here this is one combination and this is one combination. See here, Qn is equal to 1, Qn plus 1 is equal to 0. So for these values, this is the J and K values and this is J and K values. Observe here, K is fixed, K is 1, J may be either 0 or 1. So that means I'll write J may be either 0 or 1. That is nothing but don't care state. K is fixed value and it is 1. Clear? Next combination is 1 and 1. So the remaining combination which is left out is 1 and 1. That is Qn is equal to 1 and Qn plus 1 is also equal to 1. So what is the combination? Here K is fixed. See here, K is 0 and J is varying from 0. Once it is 0 and once it is 1. So it is J is don't care and K is equal to 0. So this is the excitation table for JK flip-flop. That means you will be getting the output 0 whenever J is equal to 0, irrespective of value of K. You will be getting next state as high whenever J is equal to 1, irrespective of value of K. Got it? So these are the possible combination for getting these outputs. Thank you.